Hello, everyone. Welcome back to Geology 106. The time is 2:53, and we will begin at 3 o'clock. So if you're watching this in the future, you can fast forward several minutes. But figured I'd start, as usual, by asking people how you're doing. How's everyone's week getting off to a start so far? How's it going? Oops. Misspelling stuff as I'm typing. So I'm pretty excited because today we're doing my what I like to call my Where Not to Build Your House lecture. This whole chapter is kind of a Where Not to Build Your House chapter. Not that the volcanoes chapter isn't applicable for that as well. It 100% is extraordinarily applicable here in the Pacific Northwest and actually all along the West Coast, the United States. But particularly in areas like the Pacific Northwest, where we have here on the western side of the state, we have lots of rainfall, mass wasting, rivers and streams, and groundwater and associated hazards with those three topics are extremely applicable to this area because we have so much water here. So the Landscapes Fashioned by Water chapter in our textbook, Foundations of Earth Science, is one of the most applicable textbooks to citizens here in this part of Washington. So I'm excited to be chatting about this chapter. But yeah, so looks like we have a few viewers so far. How are you guys doing? I'm happy that I have some nice tea here. Just made another fresh cup of tea. I might steep it a little longer, actually. Let's see. This is how canyons are formed. A lot of canyons are formed by movement of water, yes. Echo's doing good. Glad to hear it. I'm trying to think if there are any other processes that form canyons besides the movement of water. Probably just the movement of water. Are any of the four of you guys out there? If you haven't already answered how you're doing, go ahead and answer how you doing. Are any of you guys out there who've joined us so far? We've still got about 4 minutes to go. Are any of you guys tea drinkers? Tea drinkers like myself? I was not a tea drinker for the majority of my life. Alicia's pretty good. Awesome. Glad to hear it. Tired. I feel that. Only coffee. I'm afraid to start trying coffee. I'm afraid I'll get addicted to it and then I won't be able to function without it. Decaf Earl Grey. Nice. I'm not a big Earl Grey fan, but I do have some Earl Grey. My husband, he really likes Earl Grey, as well as English breakfast kind of black teas. But yeah, I'm afraid to try coffee because I'm afraid that I'll just get too hooked to it and then I won't be able to function without it. And it's okay. I'll just try to sleep and get all my energy from sleep. So, and tea on those occasions. But today I have a really delicious tea. I actually mix these two teas. These are so good. It's Harney and Sons vanilla black tea. Any vanilla black tea that will really do. And then I mix it with an extraordinarily sweet tea that I get from a coffee store, or not a coffee store, a tea store in the Alderwood Mall called Steepology. And this tea is called, it's their French breakfast, and it literally smells like caramel, and it kind of almost tastes like caramel too, and it's very sweet. And that's honestly why I actually mix it with the vanilla black tea, is to kind of tone down like how kind of caramely it is. But yeah, definitely caffeine is part of the college lifestyle. Caffeine before sleep. I actually didn't drink caffeine at all through college. I would just sleep and be tired all the time, right? And eat lots of chocolate. So any caffeine I got was consumed via chocolate. And I'm still quite the chocoholic too. So I think I mostly just relied on sugar rushes when I was in college. And then just being tired. Got used to it. Looks like we got a few more people who've joined us. We've got about another minute or so. So how are you guys doing? I've got at least one demo for you guys today that I'm excited about that I was trying out yesterday. So I'm excited for that. I don't know why I haven't ever actually done it before in class. I don't know, just never really thought of it, I guess. But I don't know, I'm really enjoying doing more demos instead of just showing pictures and asking people to recall this stuff happening. I'm really enjoying just being like, I know you guys know, can just see a picture, but hey, let's look at a demo of it anyways. Triggering a landslide. Kind of. You will see a landslide in this demo. So, yeah, maybe I also thought about just doing a plain like triggering a landslide, but I was like, that could get really messy. And I only have so much plant soil, and I don't want to buy more when I make a mess of it all and have to throw away some of it for the demo, or just get it all over my office. I already got a bunch of sand and dirt all over this room. Not this room, but like my desk and kind of this area yesterday, just trying out the one demo. I was like, okay, that's enough. Let's see. So let's go ahead then and get started. Again, I want to apologize for the short notice for canceling lecture yesterday. I'm not really one for excuses, so I will just apologize and say that that I don't normally cancel lectures at the last minute, and I don't anticipate doing so in the future. So you guys can pretty much count on lectures being like on the day that they're scheduled for in the future. So also there were some other important announcements that I hope all of you guys were able to see on Canvas yesterday, that originally the test was the next midterm was scheduled to be on this coming Monday the 25th. However, that is indeed a holiday, and the school does not operate on holidays, and that includes online classes. And this is an online class that is included in that. So I can't like require you guys to do, really teachers aren't supposed to require you guys to do work on those days. The submission of material, I'm not really sure what the ruling is there in terms of the submission of material, but like if it were a holiday on campus, I couldn't make you guys come in and take an exam. So I can't like make you guys come in and take an exam on a holiday in an online class either. And that's also just not fair for those of you guys who actually want to enjoy your holiday. So once I realized, kind of this weekend, I realized that was going to be the case. And I was like, I need to move that. So We will be doing lecture that day because I know that most of you guys, I already asked before in one of these online lectures, and most of you guys said that you don't have plans and are going to, that it does work better for you, for those of you who want to actually attend the live lectures live and in person during the time of streaming, so that you guys can like comment in the chat and stuff. Maybe the chat's on that side for you guys. It's on this side for me. But so I'm still going to do lecture on that day because I think it does work for most people, but I still really can't require you guys to do an exam, so I'm not going to. So we're going to lecture on earthquakes. We're going to begin our lecture that day. And then Wednesday will be exam day. And rather than like lecturing after the exam will probably be, I'm guessing 45 minutes timed again, but that may be plus or minus 15 minutes, maybe plus 15 minutes as opposed to minus 15 minutes. But depending on how long the exam is, I usually wait to write the exams till a few days before, because I want to make sure that I'm testing you guys on stuff that we have covered and that I've articulated that I want you guys to cover in the book and material. So not sure yet how long it's going to be. I won't know for like probably like a day or two before. Yeah, it'll probably be though 45 minutes to an hour. And it will be of a similar style to the last exam, where there's going to be multiple choice questions. There will be short answer questions, and you will have visual questions as well, where you'll be shown a picture and you will be asked to either identify something or make an assessment of that photo, and, you know, assess something geological about it, right? So anticipate that. And yeah, it'll, or fill in the blanks too, stuff like that. The last test is very reflective of what my tests tend to look like, with the kind of variety of different types of questions. I think that covers, but rather than, sorry, I got sidetracked. Rather than lecturing immediately after the exam, I'm going to be hosting a lecture on Thursday, because I know that most of you guys will take the exam. And if you're anything like me, you'll be like, I feel like my brain is now fried and I just need to like sit down and just space out for the next like hour. That's how I always felt after taking an exam. And I just assume that most people are similar or the same or something. I figure it wasn't too uncommon amongst the people I knew who were students. So let's just not pretend like you guys, like most people, can focus very well after an exam. And we'll do that lecture on Thursday instead of on Wednesday. So quick recap of what next week is going to look like. Monday, we're going to talk about earthquakes. We're going to start earthquakes Wednesday. And these are all at 3 p.m. Wednesday, we're going to have our exam, our second midterm at 3 p.m. And then at 3 p.m. on Thursday, we're going to finish talking about earthquakes. Let's see. Alicia, can you clarify what you mean and on what day? Is there like a conflict between one of those times? Hopefully that works for most of you guys. Also, even after exams, about an hour. Yeah, I feel like I have post-exam hangover for at least an hour. Absolutely. Honestly, mine lasts more than an hour. I'm not gonna lie. So we'll save the lecturing till after you guys have had another night's rest and you guys are maybe just not like geologied out. So I don't think I want to talk about much more unless you guys have questions. The last 3 chapters, this chapter, as well as the oceans chapter and the, what was the last chapter we did? Volcanoes. The volcanoes chapter are going to be on the test. But we have a lot to cover in this chapter, so we should definitely get started right now talking about mass wasting and rivers and streams. This chapter I normally break up. I normally teach in 3 weeks and not 1 week. So I am going to do my best to not lecture for 2 hours. Fingers crossed. I really did try to just stick with what's in the content that's in the book, though, even though I'm used to going deeper. This is a survey of earth science. This isn't physical geology. So hopefully you guys all found the link in the module for the slides for you guys. Tell me how. I'll post the link here, though, just in case you need it. There's a really quick access spot to it. How are you guys liking this kind of fill in the blank and kind of fill in some more notes on the PowerPoint? How are you guys liking that format for the PowerPoints? Is that helping you guys out with taking notes? Do you guys feel like you're learning more stuff and retaining stuff? Let me know how that format's working out for you guys and if you want me to keep doing that. Let's see. Okay, we've at least got a few confirmations of positivity there for the format of the slides. So let's go ahead and start talking about landscapes fashioned by water. We're going to first start talking about the water cycle, since this chapter really is all about water and how it interacts with geology, basically, and how it affects geology. And there's geological processes that are tied to the water on our planet. So we're going to talk about the water cycle. We're going to talk about mass wasting. And specifically, we're going to be chatting about the types of mass wasting, as well as controls and triggers on it. We're also going to be talking about rivers and streams. We're going to talk about erosion. Hopefully we'll have time today to talk about floods. We'll see. And then we're also going to be talking about groundwater tomorrow, as well as karst topography tomorrow. So that first slide there is just kind of the outline of everything that we're going to be talking about. There's also some pictures of each of the following and the hazards specifically that are associated with it. So on the top picture there, you can see a mass wasting event that's taken place. Mass wasting is sometimes referred to as mass movements. I've seen some texts refer to it as that. I've seen one text refer to it as mass movements. I am not used to calling it that, though, so I will be calling it mass wasting. But yeah, just be aware of that. So then this next picture there shows a hazard, kind of shows hazard associated with rivers. There we see a house that is built next to a river, and over time that river bank has moved closer to the house, too close to the house. And then that last picture there shows a home that has sunken into a sinkhole, which sinkholes are part of karst topography. And karst topography is a resultant kind of topography from groundwater erosion. We don't really have to worry about that too much here in the Pacific Northwest. We don't exactly have the substrate that is needed to create karst topography, limestone. We don't have massive amounts of limestone underneath our feet, so we don't really have sinkholes much out here. But we do have problems with mass wasting, and we do have problems with rivers. For any of you guys who have lived here for some amount of time, I am sure that you have been around when the Snohomish River has flooded, or maybe at least when you were a child, it flooded at some point. I know that when I was a kid, I went to an elementary school that was on the other side of the Snohomish River Valley from where I lived. And when it would flood, it was quite the task to get to elementary school because you had to go around the entire valley and you couldn't just go straight across it and over the Snohomish River Bridge. And also, like a few years before I was born, I guess the Snohomish River flooded so badly, and then it froze, like the temperature just dropped. And so the Snohomish River Valley was kind of like an iced over pond, and my folks took my older sister and they went ice skating on the Snohomish River Valley floodplain. So anyways, let's go ahead and move on though and start chatting in detail about the water cycle. So the water cycle, the hydrologic cycle, which is how your book refers to it. I call it the water cycle because it's immensely easier to say. But the hydrologic cycle is powered by energy from the sun. Yes, the sun is what makes this cycle keep moving and keep going, right? The fact that we've got that heat from the sun and that it can cause water. We're at this beautiful spot in our solar system, right? We're just at this beautiful sweet spot in our solar system, not too close, not too far from the sun, so that we can actually have water exist in all three of its states of matter on our planet. We can have ice, we can have liquid water, and we can have water vapor. So we can have it in both its liquid, or all three of its liquid, gas, and solid form here. And the only reason that happens is because of our glorious sun, our beautiful star in our neighborhood. So it's powered by energy from the sun, and we have to kind of define a few terms from here. You can see, and this is depicted quite nice and largely in your textbook. Please make sure that you do like study it. Where is that graphic? There it is. It's on page 82 in your book. And you can see that there are some quite large words on here. Specifically, we have words like evaporation. I can't actually see myself here in the viewfinder. We have words like evaporation. We have precipitation, runoff, and we have the words infiltration on here, et cetera, et cetera. And we need to know what these words mean. So let's define them for you guys. So evaporation is, as most of you guys already know, liquid water becoming water vapor. So it's water going from its liquid state to its gaseous state. So you will have water, say, like from the ocean. This is how water enters the atmosphere, right? You'll have most like water in the oceans. Sometimes it'll be in rivers and streams or lakes and ponds, etc. And the water evaporates from those large liquid bodies of water and enters the atmosphere via that evaporation. So most of the water vapor, though, in our atmosphere comes from the oceans, because the oceans cover so much of our planet. So precipitation. Most of you guys have heard this word before. Precipitation is when you take water vapor, gaseous water in the atmosphere, and it condenses and it becomes liquid water or solid water, aka rain or snow. So we have water vapor going to liquid or solid water. I can hear you guys hopefully typing away on your copied PowerPoint or in your writing down voraciously on your notes. That's not a word. So basically what happens then after like precipitation, kind of a sub bullet point, is that wind is going to then push most of that evaporated water, that water vapor, right? It pushes it from over the oceans, over the continents, right? And then that water precipitates out over the land masses. Oh, is there like click clack in the background? That's probably either the table or my chair. Very likely my chair. So OSO, we're going to talk about OSO today. We're going to talk about OSO very soon. Let's talk about infiltration. So infiltration is liquid water that has landed on the continents, in the land mass, and then soaks into the ground. It doesn't have to be on the continents, it could be an island. But infiltration is liquid water that has landed on the surface and then it infiltrates down. It soaks down into the ground. It percolates downwards, right, into the cracks and whatnot. Condensation is kind of, it is a part of the water cycle as well, but it is kind of like happens on a smaller scale. So it's not really outlined in the book so much. But let's talk about the word runoff. Runoff is very important to know about. You guys have probably even seen it happening, and you may not have known the term to give it. So runoff is water that's unable to infiltrate down into the ground, and instead it just runs across the surface of the ground, right? So it's water that's unable to soak into the ground, and it runs usually into lakes and streams. Most runoff does eventually evaporate back into the atmosphere, though. Let's also briefly define another term here that's part of the water cycle, and that's transpiration. This is not a word that I was familiar with for a very long period of time because it has to do with plants, and I know almost nothing about living things. I know a lot about rocks, though. Transpiration is water that is absorbed by plants and then released back into the atmosphere. And then evapotranspiration is just a fancy word that combines transpiration and evaporation. So it's just the combination of those two things, because transpiration is basically plants will absorb water from the ground, right? And then they will release it back into the atmosphere. So sometimes I have this big leafy plant out in my living room that's called a monstera plant. It's got these big giant green leaves on it. I will water that plant, and the water sinks down into the dirt and the soil that it's potted in, and I'll come back the next day, and if I've watered it a little too much, there will be water droplets on the leaves of my plant the next day, which is super weird, but it's transpiration occurring where the plant has absorbed that water and it's like, I don't need all this water, so I'm going to sweat some of it, right? And it releases some of that water onto its surface. And then that water that it releases evaporates back into the atmosphere. So evapotranspiration, or just transpiration. It is part of the water cycle, though. And then also we have storage of water in glaciers. So precipitation can become part of like a snowfield or maybe even a glacier, and it can serve as a storehouse for a lot of the planet's water, especially during times of like ice ages. Right now, we're in a transition period where we're recovering, if you will, from an ice age and going into a warmer period for our planet. If you want to learn more about that kind of cycle, Nick Zettner just put out an episode on Milankovitch cycles, which no one ever talks about, and they're so important, and I wish I had time to talk about them in this class, but I don't. So you can check out Nick Zettner's YouTube channel and check out his lecture on Milankovitch cycles to learn more about the interglacial and glacial periods of Earth and that transition between the two. Anyways, moving right along, let's talk about the hydrosphere. The hydrosphere is not the hydrologic cycle. The hydrosphere is just the distribution of water on Earth's planet. So most of it's in our oceans, right? Like over 97% is in our oceans. And then according to our book, 2.18% of it is not in the oceans. So where is that, 2.18% of, fresh water? Well, the majority of it is in glaciers. The vast majority of it is in glaciers. And we will get to talk about glaciers very soon. Where is the next largest repository for fresh water? The second largest repository for fresh water, you can't even see because it's under your feet. It's underground. It's in the ground beneath your feet. But we bear witness to its effects all the time. And that's exactly what this chapter is basically all about. The rest of it is, we will also talk about in this chapter, though. Sadly, we won't break them up into multiple chapters. Freshwater, lakes, we do have some salt lakes, right? There's soil moisture. Soil moisture and groundwater are not the same thing. I have another demo that I am going to be testing out, and hopefully it's going to work, and I'll be able to show you guys on Wednesday to kind of describe the difference between soil moisture and groundwater. They are different. Stream channels and atmosphere make up that last teeny tiny sliver of where the rest of our water is. So all the water that you guys see that is not in the ocean, so all the water you see on land, that's just the tiniest fraction of water on our planet, right? It's so small, minuscule. All right, so let's go ahead then and start chatting about mass wasting. Let's see, I haven't been reading the comments. Another part of the water cycle, condensation, I saw that comment. Perspiration from certain animals, exactly. We do sweat, and that sweat does, just like with plants, also evaporate and become part of, the water out of there anyways evaporates and becomes incorporated with the water in the atmosphere, right? Aquifers. We will talk about aquifers tomorrow. We'll get there. So let's go ahead and check out slide 5, right? And there's a gorgeous picture there, a sad picture, but a very beautiful textbook picture of, is it a mud flow? Is it a debris flow? For the purpose of this class, we will call that one a debris flow, because we don't talk about mud flows in this class because we are trying to condense it down as much as we can for this survey of earth science. We'll get there though. For what those terms mean. But anyways, let's just define what the heck is a mass wasting event. You keep hearing me say this term and you're like, I don't really know what that means. Is it the same thing as landslide? Kind of, sort of. Landslide, not really. Mass wasting is very broad umbrella term. Mass wasting means the downslope movement of a rock or soil or unconsolidated rocky material. And it typically moves as a mass, right, under the force of gravity. Gravity is what's pulling that stuff downhill. So mass wasting is this very broad general term, right? We're going to try and stay away from the word landslide here. I know that is what the general public tends to use. Landslide is just a very ill-defined term. So we're going to be using these more specific terms that we'll be learning today, rather than the term landslide. Although I find myself using it all the time as well, because that's the term that people are familiar with. And it's the first term I learned, even though it's kind of an ill-defined term. So I'll try to stay away from that term though as much as possible and use things like mass wasting as the broad umbrella term, or specify the different types of mass wasting. But before we talk about the different types of mass wasting, let's talk about what causes mass wasting, basically the controls and triggers of mass wasting. So on slide 6 there, we'll start going into that. So the first factor that will weaken a slope and that can cause it to give way to gravity, because gravity is always pulling downwards, right? And if you have something on a slope, Gravity is still pulling it down. And so it causes the object to move, right, like down slope as it tries to go down. So sometimes you can put something on a slope and it's not going anywhere, right? Like I can put, where's something that I can't break? A rock, right? Let's do this. So if I have my textbook here, I should get a firmer surface. Let's use this game board box. Codenames. It's a great game. It's fun. It's great for pandemics too because it's a co-op game. So and there's online versions of it. Hashtag not spons. Hashtag could be spons. Codenames. Let's take this rock here and it's on a flat surface. Gravity is still pulling down on it, but this box is strong enough to keep it from being yanked through the box. And I have it slightly inclined here. You guys can see that. It's not going anywhere. However, it will eventually if I continue to like incline it enough, right? However, here I've got it on an incline again. It's not going anywhere. I could do things though to this scenario here, this incline and this not moving rock to weaken this and cause it to give way, even though under normal circumstances, it's happy and it's fine. I could do all sorts of things. First thing is I could probably add a bunch of water underneath it. If I added a bunch of water, right, things will start to happen. Let's talk about what kinds of things happen. Water being the biggest factor that tends to influence mass movements. It's the most predominant thing. The other things that we're talking about kind of take a back seat by comparison to water. So where does this water come from, though? The water that I'm talking about. I'm not talking about me like pouring a glass of water on this. Let's talk about nature here. The water tends to come from heavy rains and snow melt, right? Oh, sorry. Water tends to come from heavy rains, right? And snow melt that saturate into the ground. And when I say that they saturate into the ground, what do I mean that? What do I mean by that? What I mean is that, oh, I wish I had my beaker here. I think it's behind me. Let me grab it really quick because it's kind of important. Sorry. Spur of the moment demo that I'm like, why didn't I prepare that ahead of time? All right. So if I fill up this beaker here with rocks, it will help me illustrate my point. I think last quarter was the first time I did this demo. I was like, why didn't I do that before? That was really dumb to not do that before. Whatever. We think of things as we go. So I'm going to grab a bunch of rocks. And soil is a bunch of teeny tiny rock grains, right? That are just teeny, teeny, tiny. So we're going to look at a really big example of that now. They're either rock or mineral grains. Okay. So I have this beaker here with a bunch of rocks in it. And you're like, okay, that's nice. Why are you showing me this? Because hopefully you guys can see that in between these rocks are spaces. You know, there's little holes in there where they don't all completely meet quite nice and evenly, you know, and that also happens. Sorry, I bumped something else. It's part of the other demo. Under your feet, the ground also has a bunch of pore spaces. The sediment underneath your feet isn't perfectly compacted and perfectly solid, right? That's why water will seep into the ground if you spill a bucket of water. It's seeping into those small spaces in between all of the soil grains. And again, showing here kind of a demo of how there's these cavities, right, in between these rocks. Just same way with the soil grains, right? So it seeps into, and in the soil, we call these pore spaces, those spaces that are kind of in between there. So water from heavy rain and snowmelt saturate into the pore spaces of the ground. What happens as a result? This reduces the friction between the grains, and it reduces the cohesion between them as well. And then what happens as a result of that, or in addition to that, it also, if I were to pour a bunch of water in this beaker, would it be the same weight? No, it would be heavier, right? Same thing happens with the ground. If you add a bunch of water, you add weight. And that's also going to be important for triggering mass movements, right? Let's see. Genesis's comment. So it's like water built up between those pore spaces. It's basically just that as the water sinks down into, say, this beaker. I wish I had a glass of water, but my glass of water is empty. I didn't refill it before lecture. Sometimes you'll just have like a little bit of water. Like if one of these was wet, there might be some moisture in there, but and that's called soil moisture. That's going to be the demo for tomorrow. But basically water will fill up these pore spaces, right? And there's a depiction of that on the slide as well. Those yellow round kind of cobbles are representative of soil grains, right? And then the first picture, there's nothing but air in between them. In the second picture, they've added some water in between the soil grains. And in that third picture, they have added so much water in there that it's more like the dirt is suspended in the water because the water is actually fully separating out all of the grains. And that's what we call super saturated, right? The middle picture there is just showing everything is saturated, meaning that all the available pore spaces that are normally there are filled with water. That's saturated. And then if I put extra water in there and there's so much water that everything is kind of separated by a boundary of water, nothing's even touching each other anymore, it's just suspended in the water, we call that super saturated. So yeah, hopefully that kind of makes sense. And hopefully it'll make sense too with the demo tomorrow as well. How the water, it just kind of finds its way into those pore spaces, right? If there's just the tiniest hairline crack, it'll find its way in there, right? And it'll take up that available space that was previously filled with oxygen. So that is water. So let's go ahead and take a look at slide 7 and talk about oversteepening. Now, oversteepening has kind of two subcategories to it because oversteepening, it's not really that it has two subcategories. It's just that there's two main points that we need to talk about. There's the angle of repose, right? And then there is exceeding that angle of repose. And so that's kind of talking about the angle of repose. And then there's just straight up undercutting. Instead of, oversteepening something, we'll just undercut the whole thing. But let's talk about angle of repose, because you hear that term and you're like, Caitlin, I need a definition, please. So the angle of repose is the steepest slope that a pile of uncemented material can attain without collapsing. So there's kind of two pictures there on the top. There's a large sediment pile there. And it shows, it looks like it's at about like probably a 30 or maybe even less. Like it honestly looks more like a 25-degree angle, right? That sediment slope there that they've been just piling high is at, and it's like that on all sides. And it's kind of like that in this cone shape because that material, if you try to if you add more to it and you try to get it to like stand up straight like this and just build like a nice little tower, it won't. It'll just fall down, right? So it's the steepest slope that a pile of uncemented material can attain without collapsing. And this is what the demo is. All right, I move my tea there. And this is why I have the board game boxes too, because I needed to build up a large stand for this to rest on. So I've got several board games and books and stuff here stacked on top of one another to make this about even with the camera. All right. So now we're going to demonstrate the angle of repose. Here I have some sand, right? And I'm going to just demonstrate the fact that basically when I pour this sand, it cannot achieve like a slope higher than about 30 degrees. It just can't. You'll see the sand grains start to roll down and roll off to the side and roll down to the bottom of the pile. And then more sand will build up on top of that. And then when it tries to like get above 30 degrees, it'll just slide down and then start building back up again, forming a larger and larger cone at about 30 to 25 degrees of a slope. So this demo takes a minute because I have to build up a big enough pile for you guys to see this, and hopefully the clarity is okay there. So let's start building our pile. All right. Let's make this pile quite a bit bigger. Let's add a bunch more sand, and then I'll start going a little bit slower. All right. Let's see if I can get this a little bit closer to the camera too, so that maybe you guys can kind of see some of the texture too, and you can see the grains actually rolling down the side of it. And you can see when they start to slide as well. It's also very difficult for this demo because they are kind of falling. So if I try to just add grain by grain and just build like on top of one another, you can see that it'll only become so steep, like I said, before the grains start to just completely roll down the side of the cone that it's forming, right? If I added some water to this and made everything like really sticky, I might be able to build like a really tall, slender tower, right? But as it is, with this material the way that it is, it can't form a slope any steeper than what I've already formed here for you guys. I can't make it like this. It has to be about this shape. I can't make a slope that's like this. Just the way that nature works. And this is, the angle of repose is different for different types of material. So if I have more gravelly material, I could actually make a steeper slope. But with like sand, you can only get it to be about like 30 degrees. So hopefully that makes sense. It might take some wrestling with the concept before it really kind of makes sense and sinks in. So take your time with that. Don't worry if you're still a tad confused. Let's see. It is due to the size of the grains composing the material, for sure. I believe that it does also have to do with the shape of the grains. If the grains are really rounded, they're not going to, they're going to roll more versus if they're more angular. They're going to be able to like have a corner get like stuck on one another, and they might be able to get like a little bit steeper. But yeah, it does have to do with the size of the individual grains of the material that you're working with. All of the grains that I am working with here would be classified in geology as fine sand sized grains. And fine sand can only achieve that like 30 or so degree angle. I do have some dirt here. Do you guys want to try it with like dirt? Let's see in the chat. Do you guys want to see it with like a bag of dirt too? Some potting soil here. If not, we'll just keep going with the lecture. And we'll take a look at slide 8. Oh, wait, no, we didn't finish slide 7. We still have to talk about undercutting. Sure, no messes, hopefully. All right, let's take a look at it with soil. Soil is a little bit different because it's not of a uniform shape, right? I better move my teacup like super far away. All right, so I didn't try this one out yesterday. I just got soil from it because the bag is dirty. So let's try making a mess here. Let's see how steep we can get the angle of repose with this stuff. This stuff kind of sticks together more, so I think we're going to get a higher angle of repose, but we'll see. Ooh, that was a very, see, it's kind of like stuck together. All right, let's try this again. Oh, I don't think it's going to work because I think it's all kind of sticky and clumps like that. Yeah, it won't work. Sorry, guys. We tried, though. We gave it a shot. If I had maybe, like, prepped a bit more and tried to get it a bit more separated, maybe it would be different. But I do have a feeling that, and you can try it at home if you have some potting soil. I recommend putting down some tin foil first because that's going to make cleaning up a whole lot easier. Versus, especially if you want to actually save your material like I do, because I'm a penny pincher. And I don't want to buy more potting soil or sand for my plants. All right, so we gave that a shot, but you guys can also give it a shot at home too if you have any material, or if you bought the really large rock kit and you want to see what the steepest angle of repose you can achieve with your gravel-sized samples. You can try pouring them into, you know, an angle there and see what happens. But anyways, that's the angle of repose. Basically, if a slope gets too steep, it's going to give way to gravity. It's only happy at such and such steepness, depending on the size of the material. If it gets too steep, that material may not be happy anymore, and gravity will take over. So undercutting, what does undercutting mean? Undercutting is the removal of material at the base of the slope. So what does that mean? That means let's bring this back here actually one more time. That means that if I come over here and I remove a bunch of material, can you guys see that? Not very well. But if I remove this material right here, did you guys see how that sand up here fell? I'm undercutting this slope, and it's giving way because I'm continuously scraping away material at its base. Let's do it one more time. There we go. Okay, enough of that. That's what undercutting is. And you'll see sometimes on like riverbanks and stuff. Let's see, where did I put my tea? I don't know. We'll find it later. You can see that like along like rivers and stuff, you'll actually see like some undercutting happening sometimes. Or if people who are building just aren't very, I don't know, they're just not thinking, they'll like undercut their like what they're working on, form an overhang, right? But this usually happens in nature as a result of water, say like water eating away at the base of a cliff, and eventually you get like this little kind of cutout, and then it's overhung, right? That cliff is now overhung, such as in the depiction there. If you make that bottom picture a bit larger, you'll see that there's kind of like an ocean or a lake or something, looks like the ocean, that's just eating away at the material at the base of that cliff, causing an overhang. There's also a photograph there on the right of a river that's eating away at the base of like a kind of grassy little hill, and it's caused an overhang. And you can even see on the right-hand side of that photo some fallen trees, because material, as it's being undercut, the stuff on top is just like, well, there's nothing underneath me supporting me anymore. I guess I'm just going to fall down because gravity works. So that's what undercutting is. So oversteepening can be achieved by either trying to exceed the angle of repose, trying to make it steeper than that that angle of repose in nature allows for. If you try to oversteepen it, it's going to be like, no, this is over my angle of repose. Nope, not doing it. Or you can just straight up undercut the thing. And both of those are kind of subcategories in oversteepening. Let's move on to the third control. Oh man, 3:48. All right, told you guys today's going to be a little bit longer lecture. But the third control is vegetation removal. So vegetation root systems actually help increase slope stability. And there's a diagram there on slide 8 showing the roots of these trees going down and how large those root systems are. And they help kind of hold things together. So if you, clear cut an area, right, you no longer you're not growing any more plants there whose root systems are kind of helping lock everything in together. And also the other thing to note about vegetation in their root systems is that they actually remove water from the ground, because the tree or the plant itself needs that water to keep sustaining itself. It's food for it, right? It's water. So it soaks up water that's unnecessary water that's in the ground, and it uses it itself, right? Or releases it back into the atmosphere. So if you clear cut an area, you're also, not only are you not like growing roots and growing more plants, right? And you've also just stopped the process of that plant removing water from the ground. Let's talk about the fourth control and trigger that is covered in our text, and that is shocks and vibrations or earthquakes. I saw Noah mentioned this control and trigger already. So a shock or a vibration can be caused by like an earthquake. It can be caused by blasting, etc. And basically, when you have a shock or a vibration, it will destabilize the slope. Now, on that slide, you see a moving picture, a GIF of Mount St. Helens erupting. And yesterday was the 40th anniversary of the eruption that you're looking at there. Mount St. Helens has actually erupted since then, but they've been like small eruptions that were not cataclysmic. So I do have to specify the May 18th, 1980 eruption, not the one that took place in the early 2000s. That kind of helped build. Volcanoes will build themselves back up sometimes if they're still active, and that's what happened in like sometime in the early 2000s. But anyways, what happened? Why do I have this volcano here? Because it was actually, as I mentioned last week, an earthquake that destabilized the oversteepened slope. The slope was pretty much becoming oversteepened. It was getting a little close to its angle of repose. And then an earthquake came along and said, it's your time to shine, Mount St. Helens, I guess. Let's see, where did I have my lovely, I'll get a different rock this time because I kind of buried the one I was using before. So let's demo that really quick. I got a rock here on my board game box. I've got it here at an angle. And that's what happened with Mount St. Helens. It was happy under normal conditions at this angle, but it's very close to the angle of repose. It's almost about to slide off the box. It's just barely hanging on. Then if I come along and shake it, then it's like, well, all bets are off now. And triggered the mass movement down. And that's what happened with the volcano, is that 1/4 of the volcano slid away and released the pressure that was building up underneath it and caused the eruption. And what you're looking at in the first few seconds of that slide is you're actually seeing the mountain slide off. That is an artist's rendition there. We have photographs that someone who was, I can't remember, it's not Johnston Ridge, but at a different spot, kind of near the volcano. He was photographing the event, and he was at a safe enough distance that he did not perish in the eruption. But he took photos, and the GIF that you're looking at there is a compilation of those photos, as well as an animator who's kind of gone in and animated the in-between shots for his clicks there. The smoke clouds are not quite accurate. The blast clouds, I don't believe those are very accurate in there. But anyways, you guys can look up more pictures of that on your own time. But that's a classic example of an earthquake, right? A shock, a vibration that destabilized a slope that was very close to its angle of repose, and destabilized the slope and caused it to give way in a mass wasting event. What else can happen with shocks and vibrations in addition to just triggering a mass wasting event? Well, if you add water into the situation, you can actually push and then you shake it, just like what's in that picture down below. You can actually start to liquefy things. Who here has ever heard of liquefaction before? Go ahead and sound off in the chat if you've heard of liquefaction before. We're going to watch a video. Yes. I love showing videos of liquefaction in my classes because most people have never seen it. And it just weirds everyone out. It's my favorite. I love doing that. I really love blowing people's minds with science. So I have a link here that I'll put in the chat as per you guys' requests last time. You guys were like, yeah, post the link in the chat. First, okay, so it seems like all few of you who were able to join me on this Tuesday, seems like none of you guys may have actually heard of liquefaction before. So there's the video link in the chat if you guys would like to watch it on the side. Highly recommend doing that since this is not the highest quality here. But I will show it for those of you anyways. Let's turn up this volume. Maybe not that loud. That's a little loud. All right. So let's go ahead and watch this.
Little liquid earth. Here, hold this and just watch. Just shine right at the bucket when on it.
Can you guys see that?
Wow, that's fucking...
Sorry about the F-bomb. Thankfully, I'm not in this for the monetization. There we go.
Wow.
Liquid earth there.
That's crazy. What is in there?
Just water.
This is some goofy stuff.
Goofy stuff indeed. All that's in there is water in between those grains. And they're serving as the shock and vibration there that's causing the water to kind of push apart all the grains and causing it to behave somewhat like a liquid. This happens in earthquakes too. And we will talk way more in depth about liquefaction I'm planning to talk more in depth anyways about liquefaction next week. And we'll look at some videos that actually are kind of scary. Indeed, as Alicia says, from the Tohoku earthquake that occurred in Japan. Oh dear, I forget the year, but kind of in like I want to say somewhere around like 2010, maybe? Nah, yeah, sometime around 2010, give or take several years. It was the earthquake in Japan, some of you guys may remember, that caused the nuclear meltdown in one of their power plants and in Fukushima, right? And it caused that nuclear fallout there in Fukushima. However, the earthquake itself and not the like nuclear event, the nuclear event is referred to as like Fukushima. The earthquake, though, is called the Tohoku earthquake that caused all that. We will talk more about Tohoku next week. And 2011, thank you, Noah. So yeah, that took place in 2011. We'll look at more videos of liquefaction later. I'll also post another video for you guys to watch that I didn't have time to quite sneak in there onto the Canvas modules, but you don't have to watch it. It's really just for funsies because this stuff is wild. It really is wild to see that kind of stuff. So that's what happens when you add water into the system, when you add shocks, and when you're talking about shocks and vibrations. It doesn't always happen. It really does have to be just the right amount of water to the amount of soil, right? And the type of material that you have. So you don't always see this occur in earthquakes and in areas where there are water. It does have to be kind of just the right recipe, but it does happen. And we've seen it multiple times in multiple places around the planet. Let's go ahead and take a look at slide 10. And now we're going to talk about the types of mass wasting that are covered in your book anyways. I originally was thinking that we were going to talk about avalanches right now and like the wet and dry avalanches, but your book doesn't actually cover wet and dry avalanches as part of mass wasting. The other book I teach out of for physical geology does cover it. But we have so much to cover in this chapter anyways that if we have time to talk about it when we're talking about glaciers, we'll talk about it then. So let's just talk about the 4 types though that are covered in our text. So slump is the first type. And basically slumps these are all characterized by just the different way that the movement takes place, the different kind of material that we have, and different conditions will cause different things. Different landscape morphology is going to control also what type of mass wasting event takes place. But we have 4 types. We have slumps, we have rock slides, we have debris flows, and we have earth flows. Now, some other additional types that I won't be testing you guys on in terms of being a mass wasting event and that your book doesn't really talk about, but we learned about lahars last week, and those are actually considered to be a mass wasting event that is caused by either heavy rain or rapid snow melt or just an eruption. And then there's also avalanches. And there's probably a couple others I'm not thinking of. But we'll just talk about slumps, rock slides, debris flows, and earth flows for now. Actually, we're really not going to talk about earth flows beyond what's on this slide. So a slump is downward sliding of mass or rock, an unconsolidated material, moving as a unit along a curved surface. So what do I mean by that? If you look at that block diagram, there's like this curve at the base of the slope, and that's the surface along which movement is taking place. And it really is like a rotating kind of thing almost. And a bunch of the material gets kind of pushed down, and you see these blocks kind of like separate out as the whole material kind of like rotates. And it really breaks up into these very, very large blocks of earth that kind of slump downhill when this movement takes place. So keynotes here is that it's moving as several large units that have broken into blocks, right? And it's moving along that curved surface underneath. Let's talk about debris flow next, because that's the order I put the following slides in. Debris flow of weather debris. You know what? Let's just go ahead and I'll dissect these more as I go down. Earth flow, except I'll do that one now because I don't have another slide for it. Earth flow is kind of this tongue-like flow of water, saturated clay-rich soil on like a hillside that breaks away and moves down slope. I saw like a really insane video of an earth flow once on YouTube, and I will try to find that again and post it in the module here so you guys can get a visual description of an earth flow. I couldn't find it before a lecture, but it's one of the most insane things I've ever seen. So we'll talk more. I will define debris flow and rock slide in just a moment. But I'm kind of going to save the details for when I hit the slides that are just dedicated to them. So let's talk about slumps and talk in detail about slumps. Go ahead and go on to slide 11. So the 2014 OSO event was classified as a complex slide that was both a slump as well as had some elements of a debris flow, which we'll define very soon. Let's just talk about the slump portion though of the 2014 OSO event. Who here remembers the OSO landslide in 2014? Okay, so Alicia remembers it. I was in grad school at the time when that happened. It was just crazy. I remember being on campus and people were like, "Did you hear about the landslide?" And I was like, "What?" And I didn't understand for a little while the magnitude of what took place until I saw it. But let's see. So yeah, we have several of you guys actually remember the OSO landslide. I have taken students out there to see it, and I was going to take students this year to see it too, but it rained so much this year that like in the fall and in the winter that for my class last quarter, I was like, we're going to skip OSO. It's just rained too much. That's the recipe for disaster is adding water. It would probably be fine. And obviously it hasn't moved yet. So I think we're fine, but I'm extra cautious because I'm not an expert. So looking at those photographs there though, that are on this slide, you can see this massive like headscarp there in the top left photo. And a headscarp is basically that bare surface that's kind of sloped downward fairly steeply. And it's just like that sediment that you're looking at there. That's the headscarp. And then you see these chunks of earth down from the headscarp that are almost like stairs, you know. There we go, going down, stair stepping. And there was a lot of water in this hillside at the time. And the very edge of the slide, the very toe of it, did kind of liquefy and become more like a debris flow. But there's a before and after picture there on that slide. There's also an amazing LiDAR photo there that is very colorful. So you see this gray photo that's got a bunch of blue and yellow and green and red, pinkish red on there. That photo is basically they've removed all the vegetation from that valley where the OSO slide took place. And they've color coded all the different slides that have occurred there in the past. So this valley, do not buy property there. If you know anyone who has property in that valley, tell them to move. It's just not a safe valley to live in. So anyways, I'll let you guys look at that later. Moving on though to slide 12. There's a beautiful illustration there showing the labeling of the headscarp You can see how the hill slope has broken up into different blocks and slumped down that curved slope, kind of like slumping in your chair, right? And then you can see that at the very edge of that slump, we call that the toe of the slump. And that's the part in Oso that kind of like liquefied and became more like a debris flow. And then there's just some photographs up above on slide 12 showing you those headscarps, right? And how there's different like blocks of earth, you know, that are kind of going down like stairs, sort of. So hopefully that does give you guys, I really want you guys to be able to see these different slides and be able to recognize them based off of like looking at a photograph, like, oh, wow, I see a giant headscarp and I see blocks of material and kind of this bunched up toe at the end of it. That must be a slump because those are, you know, characteristics of a slump mass wasting event. So hopefully, so really study these up and kind of get familiar with looking at these pictures. Let's go ahead and look at the next kind. Will they be on the exam? They could be. I am a big proponent of visual questions who puts things on there and is like, tell me about this photo or what's in this photo or what is this thing, you know. So it would be a good thing to study for sure. And potentially be on the exam. So let's go ahead and look at slide 13 and start talking about the next type of slide, haha, that's a pun. Anyways, let's go ahead and talk about the next type of mass wasting event, mass wasting type debris flows. So looking at some photographs there, what I want you guys to notice is that all of these are very long and skinny, right? All of the pictures that you're looking at, the movement, it's usually along a really steep slope that's it's usually confined to a channel, and it's more like a slurry of mud. We have lots and lots of water making kind of more like this, yeah, like a slurry of sludge and kind of like cement. Very similar to a lahar, except this is not volcanic material that we're dealing with here, such as like ash or tephra, volcanic tephra. This can happen away from a volcano, but it's a very similar process and it behaves very similarly and it looks very similarly. It's just not necessarily composed of volcanic ash and volcanic tephra, but it's pretty much the same thing. They look like walls of flowing cement down a river channel or down like a valley channel. If you're ever driving in the Cascades, like if you're going along Stevens Pass or Snoqualmie Pass, or if you're hiking up there in the Cascade Mountains, keep your eyes peeled as you look at the various steep mountain slopes around you. It's not uncommon to actually see these in the Cascades. I've seen many of them just driving from Eastern Washington to Western Washington or hiking up there in the Cascades. So confined to a channel is a very key defining factor of a debris flow, as well as that it's usually very water saturated. Not just water present, because usually water is present in most of these, but in most, not always. But these are like very saturated with water. Thick, muddy slurries. So let's go ahead. Not that they can't also, by the way, carry things like large boulders or vegetation. They totally can, but there's just a ton of water. So anyways, all that stuff's just mixed in with a bunch of water. Let's look at slide 14 and talk about rock falls. So I don't have a slide dedicated to earth flows. I'll send you guys that one video and that will be like the extent of talking about earth flows, but let's chat just a bit more in depth about rock falls. And there really isn't a lot to talk about in depth about rock falls because it is about as simple as it sounds. Rock falling. We're talking about like, you know, just solid rock. We're not really talking about loose unconsolidated sediment here. We're talking about chunks of rock that have eroded off of their cliff. They've kind of been separated and, cracks have formed over time. And then eventually they give way to gravity because they're no longer connected to the slope, because weathering has taken place and it's been breaking these rocks down into smaller bits, and they're no longer connected to the hill slope. And one day, either like a shock or a vibration, or perhaps some water has gotten in there to help lubricate things, etc., etc. In any case, a rock fall, though, is when you have blocks of solid rock that fall down slope and fall downhill. So you can find so many pictures of rock falls taking place on roadways. Whenever you Google like rock fall on on Google Images, you mostly see roadways with rocks on them. I think it happens elsewhere, right? But I think that because of the way that we construct things here in more like first world countries, that rock falls just tend to commonly occur along those areas. I don't know. Anyways, let's go ahead and take a look at slide 15. Where not to build your house is what this is called. So this is the slide where I tell you things to look for when you're looking at buying property. And I love doing this so much. So go ahead and make those pictures like pretty large so that you can see what we're looking at here. Kind of the main things that I want to point out to you are actually on the right-hand side and then the bottom left photo. The top left one is just there for shock and awe. But what we're looking at here, let's go ahead and start at the bottom left, and we'll go left to right. At the bottom left there, you see a fellow behind a house, and there's like this kind of retaining wall. And there is a slope behind him that is pretty steep. And part of it is bare and free from vegetation. This is not a good sign if you were looking at buying that probably adorable cabin that's there. The retaining wall being present means that they're trying to keep debris from falling onto the property. The fact that the slope is bare means the movement bare from vegetation means that movement has probably taken place very recently and removed any vegetation that was there. Also, vegetation does just have a hard time growing on really steep slopes. It has trouble putting roots in and taking seed on very steep slopes. But just looking at that and how there's nothing on top of that slope, it looks like movement has occurred recently there to me. And also the fact that the slope is just extraordinarily steep and you have vegetation above, and then it reads stay away. Don't build here is what that reads. Don't buy property here. Let's go ahead and take a look at the photo on the top right, which is a diagram that has been drawn showing at the very top, there's like a road, and then there's kind of like some fill and then natural slope and then a cut down, and there's a house. They also have like a little dashed line and circle coming off of that house. That's a septic system that the illustrator put in there. And then you go down another slope and there's yet another house with a swimming pool there. Now, let's just chat a bit about, there's a lot to unpack here. Terraced hills can sometimes help prevent mass wasting when done properly. When not done properly, they can encourage mass wasting because you've oversteepened. If you like cut way down, you can just leave an incredibly large oversteepened hill. If you're like making kind of like really intermittent gradual, moved the cookie sheet with all the sand and dirt on it. If you're making like really kind of closer, like stair steps, right? That can be safer. I also don't want to freak too many people out here and just be like, never live on a hill. I live on a hill. And I feel pretty safe living on this hill. A lot of my students get out of my classes and they're like, I'm never buying on a hill. It doesn't mean that you can't buy on a hill. I live on a pretty steep hill too. And it's fine because it's not past its angle of repose, right? Anyways, this terracing looks like it's done okay in this photo. It's kind of steep. It's not quite my favorite. But there are some problems, though, in this photo, such as the septic tank and the pool. The septic tank and the pool, if those leak, they can add water to the ground. Also, these houses built on this slope, remember that houses and other things add weight to slopes. So if you are going to be building on a hill, you really need to understand and make sure that you've got the right balance, that each terrace is kind of wide enough, right? That if you build on it, you're not going to be adding so much weight to like a really narrow slope, right? And then everything just slides down. Really has to be done right. But again, you want to be careful about adding weight to slopes and adding water to slopes. You also want to be really careful with your road cuts and to make sure that you're not over steepening the slope that you've cut into. We see this all the time, though, happen where people do build improperly and they do cut the slope too steep and too tall, and they over steepen it, and then stuff just gives way. Right? So you want to be careful. The bottom picture there shows an extraordinarily expensive home, probably a mansion that was built with a beautiful view. Homes with a view tend to come with a cost, but and this person is paying a very high cost for their view. They're losing their house because this cliff is actively eroding away. And it eroded away right underneath their house. So building on a cliff, not a good idea. We see it done all the time, though. You see it done everywhere around here. You see it done like particularly near the waterfronts. You'll see homes built on cliffs, and there are plenty of homes that I see, and I'm just like, I would never buy there. Yeah, this is one such home. I would not buy there. Nope. You see an actively very weathered and eroding cliff face. It's probably not a good idea to build there. Let's see. Let me catch up on the comments in the chat. Who authorized those building permits? Will this be on the exam? So basically, if not done carefully, it could be artificially induced undercutting. Absolutely. We'll look at, I've posted a video for you guys showing several landslides, and one of them is a building project that's in, I'm not sure what country it's in. It's in a different country, though. They don't speak English there. It's not the primary language, because they're definitely speaking a different language in the video, where they are building things improperly, and you see this heavily eroded and oxidized soil cliff just give face, and it's because they're building improperly and they've artificially undercut and oversteepened the slope. Let's see, who authorized those building permits? I would love to know. It's one of the sad things about building is that there is not, for example, with OSO, back, I can't remember what decade it was in, whether it was the 90s, 80s, or 70s, but in any case, geologists had gone out there and they had done studies and surveys of the land, and they had said, this is a landslide prone area. Don't build here in Oso Valley, where that landslide took place. And they did it anyways, a few decades later. built there anyways. So there really is a problem, is what that means in terms of geologists going out and saying like, hey, we did a survey here, we looked at everything and this isn't safe, don't build here. And then builders going in and still somehow being able to build on the land anyways. And then either because they're not doing their research, they're not getting that information from the geologists maybe, or they know and they're building there anyways, I don't know. And then they're selling it to people. And if this builder doesn't know and the real estate agent doesn't know, or if the builder knows and then doesn't tell anybody, then there's clearly problems here. So something's not right in the system. Hopefully, my job as an educator is to tell more people about this, and hopefully I will inspire a student to be like, I'm going to fix that. And then become like, I don't know, a politician or something. Anyways, let's go ahead though and look at slide 16. Again, aware not to build slide. This photos here are from 2 years, except for the bottom left one. I don't know where the bottom left one is from. But anyways, the other 3 photos on that slide are from Rattlesnake Ridge, which began moving 2 years ago in 2018, I believe. There's a large crack in this hill slope that you are seeing depicted here, right? And it's wanting to slide and give way. I'm not actually sure that that LiDAR there is from Rattlesnake Ridge. That LiDAR might not be. But in any case, there's a mining company that's there, mining gravel out of that hill slope. That's in Union Gap, if you guys know where Union Gap is in Eastern Washington. And there's a very important highway that goes through there. There's not a lot out in Eastern Washington, including roads. And that road is like, there's not really a very good alternative road for the highway that goes in there through Union Gap. It's pretty much the only road. If you want to like go a different way to get to other places, it'll take you hours. This mining company has, in my opinion, they're the ones who've destabilized this slope and also just probably the road cut itself. It's just not an excellent place to build a road. It looks like it though, because it's a wind gap, and we're not going to cover those in this course, but it was not a good place to build. And the mining company says, it's not my fault, and it's like, pretty sure it's your fault. It hasn't slid yet. It hasn't given way, however, and I think that the crack in the hill, which is quite a large propagated crack, has stopped moving, but who knows? Let's not spend too much time there on Rattlesnake Ridge. If y'all want to ask me questions though, at a different time outside of live stream, I'd be happy to answer questions. It won't be on the exam. It's just a curious case that exists here in our state that's, I don't know, interesting to talk about. There isn't another road. Echo, have you actually driven past through Union Gap and seen it? I accidentally took this road last summer when I was driving with students to Oregon. I wasn't paying close enough attention to the driving directions, and I was just kind of, doing the thing, just going where the direction where Google told me to go, and Google took me through Union Gap, and I was like, well, students, here's a learning opportunity. Let me tell you about that terrifying scene that we're driving past. Not my favorite, but they got to see it anyways, and it was totally dry, so there wasn't any water present. So if there's a good time to go through there is when things are dry and there hasn't been a lot of rain. So in any case, let's go ahead though and take a look at slide 17. Let's look at preventing mass movements, revegetation. Revegetation is one of several ways that you can help prevent a slope from destabilizing, because as we already talked about, vegetation, if you start planting stuff, the root systems will grow and they will help hold things together, and they will also remove excess water from the ground. So it doesn't mean that if you have plants there that mass wasting can't take place. It just means that if you have an area that you're concerned about and you want to maybe help mitigate, you could start planting some plants, and that might assist with stabilizing a slope. So slide 18 details a few other mass wasting prevention, a couple more mass wasting prevention techniques. They look very similar, the two diagrams that are there, but they're not actually quite the same thing. Retaining walls, which is actually the one on the right-hand side of the slide there. A retaining wall is a barrier or a wall that you build at the base of a slope that is meant to trap rocks and sediment that's falling down behind it. So that's a retaining wall. And then fencing or coating is literally where you take stuff like cement and whatnot and you cover the face of an outcrop so that small loose rocks and material won't fall down and begin accumulating at the base. I am assuming that this also helps with erosion, although that's not in my notes. Excuse me, but I'm assuming that it kind of helps prevent further weathering on, like, say, a rock face or something like that. So those are retaining walls and fencing or coating. Let's go ahead and take a look at slide 19. So some other engineering structures that you could build would be ring nets. You can actually see these at least on Snoqualmie Pass. I haven't been on Stevens Pass in a long time. But I have seen these in the last like 5 or 7 years at least on, I'm not sure if they're still there though, on Snoqualmie Pass. These ring nets are basically flexible fences, and all of those rings are designed with excess like coiled material, right? And they expand when a large rock or boulder or something falls into the net. And they expand to accommodate stretching to allow it to be able to hold that large boulder or rock that has fallen. And that's what you're seeing depicted there is a large boulder that fell into one such ring net, and all of the rings have stretched in order to accommodate just elastically stretching to hold on to it rather than just breaking. There's also rings too in the cables that hold the fence in place. You can see kind of these cables going off of the fence and anchoring it into the ground behind it. Those also have rings, like I just said, to accommodate additional stretching there of the fence itself, not just like the, netting in between the fences. So these are actually really awesome. So ring nets are flexible fences that hold back large debris, things like rocks. Not good for sediment. Good for rocks, not sediment. So look at slide 20 and talk about a couple other engineering structures that can help prevent mass wasting. Let's talk about rock staples or rock bolts. The diagram calls them rock bolts. I refer to them as rock staples. Both terms are acceptable and mean the same thing. Basically, what happens is if you have rock that is fractured in there, they call it a joint. Subtle difference. We're not going to talk about it. Anyways, you have like a really heavily fractured rock surface. If you drill these bolts into it, you're going to basically screw down those fragmented joints of, rock surface, and you're going to just, kind of like a staple to a sheet of papers. You're going to staple it down, right? So Rock staples are rods that are drilled into rock to hold loose facing, just staple it down. Let's talk about avalanche sheds, sometimes referred to as snow sheds. I've only ever in our state colloquially heard them referred to as snow sheds, but avalanche shed is probably just a more descriptive term. We used to have one as well on Snoqualmie Pass, but they've done in the last 8 years a lot of road construction there, and they've rebuilt the road and taken out the avalanche shed, and they just built the road up high so that the avalanche, rather than going over this kind of like tunnel that they build, and it just goes over the tunnel that your car goes through on Snoqualmie Pass, they just built the road up. So now the avalanche just goes under the road, under the bridge that the road is built on. So avalanche sheds, a nice concise definition you could give to it, is a structure that averts avalanche snow over a roadway as opposed to onto the roadway. They also have, I heard a military tank up there somewhere on Snoqualmie Pass to help, might be Stevens Pass, to help trigger avalanches when they're doing avalanche control. I thought that was awesome when I heard that. But anyways, all right, 4:34. All right, let's stick with me, all 8 of you guys, just a little bit longer. Let's go for another 25 minutes and talk about streams, and let's see how far we get with today, and we'll pick up tomorrow wherever we leave off. So it's pretty obvious why we want to talk about mass wasting events, because when you're building infrastructure, you don't want a mass wasting event to cause the loss of infrastructure, the loss of life, etc. It's very straightforward. But now we're going to switch gears, and we're going to start talking, about streams, right? Oh, hold on a second. I think my slides are about to get off from your guys' slides. My numbers anyways. Hold on, let me check. Aha, they are. Let's make sure that doesn't happen. And duplicate that slide. So on slide 21, you're seeing kind of a blank slide there that asks at the front of it, why should I care about streams? And now's a great time to ask you guys who haven't looked at the next slide yet, don't look at the next slide, to think up and brainstorm some ideas of why we should care about streams. It's a bit more abstract because you're I don't know, walk by it, it's there. But what are some reasons why we should care to study about these things? Anybody in the chat want to venture a guess? The sooner you guys venture a guess, the sooner we get done with lecture. So let's at least see 1 or 2 people venture a guess down in there. Streams influence mass wasting? They do. So in addition to that, also water is key to life. Water is very key to life. And it is a reason why we should care about streams as well. So thank you, Alicia and Echo. Let's go ahead and take a look at slide 22 and actually read up on some of those reasons why we care about streams. Streams carry water and nutrients to various parts of the land. Say it rains up high in the mountains, the stream comes down towards the ocean. It's going to carry nutrients with it from the highlands all the way down, and that's going to be able to feed various ecosystems, animals, etc. And it's also, rivers and streams are habitats for different plants and animals and things. Also, rivers and streams drain excess water out of various locations. So if a lake floods, it would be really nice if there's a river or a stream coming out of that like lake that's flooding, because then that stream can carry water, excess water out of there. Also, rivers and streams carry excess water that is seeping from the ground. So groundwater maybe finding its way to the subsurface and then subsurface to the surface, right? And then find its way into a stream. So drains excess water. Also, we care about streams because streams themselves do carry hazards with them. Streams erode over time. I know it seems kind of abstract because you're like, but I've driven over this stream near my house like a million times and it looks the same. Well, not all streams look the same, and eventually the stream that you drive near all the time will change as well. So erosion and also floods. Streams and rivers flood. So those are just two examples of hazards that are associated with rivers and streams, and also energy. Rivers and streams serve as energy sources. If you set up some sort of turbine or mill there, and the water turns the turbine or mill, and you can generate energy there and convert that energy into electricity, etc. So that's why we care about rivers and streams. And that's why it's good to know about them, so that when you buy a house near a river or stream, you know the hazards that are associated with it, stuff. And also, in case you're trying to harvest energy, let's talk about the various zones along a river. So go ahead and look at slide 23. This shows kind of the progression on a large landmass where you've got really high above sea level mountains, right? And then it goes all the way down, right, into kind of an intermediate area. And then the mouth of that river is probably, they didn't draw like the ocean there, but it's probably like emptying out into an ocean right about there. So we can divide this into kind of three major zones. The headwaters of a stream are basically where all the water is coming from that empties out into a stream or a river. So usually headwaters are found in the mountains where rain is falling down and it's finding its way into these channels, or snow that's melting or falling finds its way into these channels and then flows downhill, and all of these various drainages kind of come together and form one large stream a bit further downhill. We call that area, though, where all that water is collecting, initially coming from the headwaters. Then there's the stream trunk, right, which is that main stream. Once all of that stuff is funneled into one large channel, we call that the stream trunk. And then the mouth of the river is where the river spreads out and usually empties into like an ocean, or say like a lake or something like that. And we can also define these three parts of the river: the headwaters, the stream itself, basically, and then the mouth. We can also classify these into different zones. We can call them the zone of sediment production, aka the area where the water in the stream is eroding material and is grabbing material to incorporate it into its water and carry it downstream. We can then break up the middle section into the zone of transportation, where sediment has already been picked up from the headwaters, where there's a lot of high energy going on, picking up stuff. The zone of transportation is kind of where the river is kind of like happy as it is, and it's just carrying the stuff that it has. And then the zone of deposition is where the river finally starts setting stuff down. It picked it up in the headwaters, carried it through the zone of transportation, and then it finally dropped its baggage in the zone of deposition. So slide 24 there, we're going to talk about this now in terms of velocity. Velocity meaning how fast the stream is going. High velocity, the stream is usually in a high velocity, has a high velocity in the headwater area, in that zone of sediment production, right? It's very steep up there. So basically that steep slope is what allows the stream to move so quickly. So if I like have a really steep like game board box that I'm tilting and I pour some water on it, that water is going to run down that slope very fast. And if I reduce the slope a little bit and pour water, it's not going to run down that slope quite as fast just because the slope's not as steep. And you can also illustrate this the same way where if I have a rock serving as like a water particle. Let's do this too. Another on the spot demo. So if I have a rock here, that moved pretty slowly, right? Versus that moved a lot faster. So if you have like a steeper slope, as is usually the case in the headwaters, your water is going to be moving a lot faster. And it's also going to, if it's moving faster, it's usually going to kind of give whatever stream bed it's going through a beating, and it's going to break up the stream bed into smaller bits and pieces, and it's going to carry like bits of sediment and rock from the bottom of the stream bed. It's going to pick it up and it's going to carry it with it downstream. So that middle zone of the stream, that zone of transportation, usually has kind of like a middle ground velocity. It's not too fast, it's not too slow. It's kind of like medium velocity. And this is where the stream is just transporting sediment. It's not necessarily picking up new sediment. It's not necessarily dropping the sediment that it is carrying. It's just happy with what it's got and it's taking it with it. And then low velocity. So the streams is usually at its lowest velocity at the mouth of the stream, or the zone of deposition kind of area of the stream. When the stream isn't moving as fast, it can't carry really large particles anymore, and it begins to drop the bigger stuff. And then as it loses more and more velocity, more and more energy, it's like, well, geez, now like, you know, so say it dropped a really big piece earlier because it slowed down, and it's like, well, I just don't have enough energy to keep this picked up anymore. And it, you know, this falls and settles out, right? And then, but this guy is good, so it keeps going further downstream. Eventually, the stream might even be moving slow enough. It may have lost enough velocity that it can't even carry this in it anymore. And this settles out, right? And then say you have like, you know, little dust, you can't see it, but I have sand in my hand. Little dust particles or sand-sized particles, those can travel quite a bit further, still suspended in the slightly calmer water. But if the water stops moving, it's not going to be able to carry that dust or silt or sand anymore. And even that will begin to settle out. And that all takes place in that zone of deposition where there's low velocity. It happens downstream, right at the mouth. It just can't carry the sediment anymore because it's moving too slow, and deposition occurs. And yes, runoff goes into streams. I see Avi's comment there. I just caught that, sorry. Let's go ahead and look at slide 25 and check out kind of those early stages of stream erosion. We'll go for just a few more minutes here. So early stream erosion, down cutting. What the heck does the term down cutting mean? Basically, down cutting is, like I said, how you erode the bed of the stream channel, the river channel. Water is basically just like blasting through there, and it's beating against the ground, and it's breaking off bits and pieces and whatever of sediment from the bottom of the channel, and that's going to deepen the channel over time, right? As a result, you end up usually with these V-shaped channels in the headwaters area in the mountainous regions. More info on that in your textbook. Be sure to read up on down cutting and kind of the V shape of channels. It's also a focus question. And basically how this happens, this can also, this erosion from the bed of the channel can also happen because you have, you know, sediment and stuff. Sometimes it is, if this is the bottom of my stream channel here, sliding along it, and it's scouring the bottom of it, you know, scraping up bits and pieces of it. So if you have sediment that's sliding along the bottom of it or rolling along the bottom of it, you're going to produce more sediment and pick up more stuff. And then that hydraulic power of the fast moving water also helps to pick up that sediment. So basically the two things there that cause the down cutting is going to be the sediment itself, either rolling or sliding along the base of it, or the hydraulic power of fast moving water down that kind of steeper slope. So that's kind of early stream erosion. We will also talk more, by the way, well, we won't probably have time to get to it today, but we'll talk more about that diagram on slide 25 in the bottom left a bit more tomorrow. Let's talk about streams, though, that have down cut until they reach base level. What is base level? Base level is basically, it's like where the stream is happy. And it's not down cutting anymore. It's like, I have finally eroded the bottom of my river channel to a point to where I don't have like a really high stream velocity anymore. I've evened things out. Now I'm just going to be like really still and calm going along. So that's kind of like what base level is. It's like, where is the stream gradient happy, basically? Ultimate base level is typically sea level. So a stream will erode and continue to cut down its channel. Hopefully it'll keep trying until it reaches like sea level, basically. Sometimes streams and rivers can be happy, though, at a temporary base level, which is like if a stream empties into a large lake, it will be like, oh, hey, this is nice. I'm happy here, and I'm not going to be eating away at the base of my river channel anymore, right? Our stream, let's see, our major river here in this area is the Snohomish River. And I also have a picture of Everett there on slide 26, showing the Snohomish River kind of going around Everett, right around like downtown North Everett, and then emptying out into the Puget Sound. And our river, the Snohomish River, at least around where we live, is at base level. It's not really eroding down its channel anymore. It's not digging up stuff any longer. So what happens, though, when a stream does reach its base level? Let's take a look at slide 27. What ends up happening is valley widening. So rather than focusing what energy it has at the bottom of the channel, it's going to start focusing it side to side on either side of its channel. And this causes valley widening. And that diagram there on slide 27, thank the Lord I found that on Google because it's far better than anything I've seen in any textbook there, describing valley widening process. Basically, once that stream's base level is reached, stream's energy is directed side to side. And then you begin developing stream meanders. What are meanders? A meander is a bend in the stream that's caused by that side-to-side erosion. So you see in that diagram there, I think this will probably be where we'll probably go one more slide today, but you can see in that diagram there how the stream is eating at one side of this stream, and then a little bit further down, it's eating at like the other side, and it's causing the stream to develop this rather than just a straight line, it's kind of snake-like, and we call that like meandering, right? Where there's this bend here and then a bend there, and it causes the stream to meander. And stream meanders, these streams at base level will continue changing their shape. So that meander will meander over time. And that's why we call it meander too, because they just like go all over the place, wandering around, not aimlessly. There is a pattern, and I'll try to kind of illustrate that more tomorrow when we meet. And I'll just briefly go over the points cut bank. This will kind of get us started for our conversation tomorrow. And cut bank and point bar, we should define these terms. They're extraordinarily important. Cut bank, the stream's velocity is highest at a cut bank and it erodes. But I still haven't really defined the term cut bank for you guys. I don't know why I have that bullet point that says that without actually defining the term cut bank. Let's grab this here. These will be the last two things that we'll go over today, is cut bank and point bar. So I have a meandering river channel here, and I will draw arrows showing the flow of water. So this is upstream, and this is downstream down here. That says upstream. So I've got my river channel here going down, and as the water is going down this bend here, it's going pretty straight, and it's like happy, hey, I'm going down this nice channel here. Then all of a sudden there's a bend in the river, and the water's like, I thought I was going straight. And it runs into this side of the river channel where the bend is. And it does eventually be like, well, I can't go there. I guess I'll just go down, and it does keep flowing downstream, right? However, what happens as a result is that this area, I'll use a different color here. This area here gets eroded back because you continuously have water crashing into this side of the bank, and this river bank here is it's going to take a beating, and it's going to lose sediment and rock and material to the river as the river's punches it basically right there. So that material goes with the river, downstream. And so the water's like, hey, that was nice. And now I'm going straight. I'm going straight again. And then it runs into this side of the river channel. And when it crashes into this side of the river channel, it's going to also continue to wear away and dig into this slope. And it's going to cause it. The stream channel is eventually going to there goes my orange pen. The stream is eventually going to cut away, and it's going to, as a result, widen this channel over time. It's going to widen that spot there. And this spot here will also widen. Right? But that's not the whole story here. The story does not end there. We need to talk about what happens in the other part of the stream. Whoops, that lid is stuck on there. We need to talk about what happens right here and here, because the exact opposite ends up happening. I'll just erase it with my finger. I know my diagram's getting messy here. So let's talk about those two spots. What happens is that the river's going pretty fast over here on this side, and then the water is pretty slow over here. The water actually loses velocity in this area. And what happens when a river slows down? When the river slows down, it can't carry anything anymore because it's lost a lot of its energy, and it's like, well, I suddenly can't carry this guy anymore, and it settles out. So what ends up happening is you get deposition occurring here. Those are deposited rock and sediment grains. So you have erosion taking place over here, and then you have deposition taking place over here on the other side of the river bend. And what's going to eventually happen over time as a result of that is this will build up above, it'll reach like the surface level, it'll just keep piling up more and more sediment until it becomes part of the river bank. And the water's not going to flow over it anymore. The water's going to flow around all the stuff it deposited. And you end up moving the river channel over time further and further this direction, right? So I deposited even more stuff there. So the river has become even more sinuous over time, and the same thing's going to happen down here too. Keep depositing more stuff. Just move the whole river channel over. So now this stream, when I first drew it, was not quite so zigzaggy. It was kind of more gentle. But the stream over time is going to become more and more sinuous just because flow velocity is going to be really fast here, and it's going to be really slow here on this side. And deposition, erosion, it's just how the process will continue over time. And it is 5 o'clock, and that'll do us for lecture today. I see that Noah would like to do a live chat. If you would also like to do a live chat right now after this for questions that you might have about content or material that we covered today, go ahead and leave your name in the chat. I will leave this up for probably 2 more minutes. Just to make sure that I catch anyone else who wants to get in on the live chat Q&A session. Just to make sure, because I know there's a lag and I don't want to miss anyone because that's happened before. So go ahead and put a comment there in the chat if you want to do kind of a live Q&A session. All right, and if you don't want to do a live Q&A session, have a great evening, and I will see you guys tomorrow. So let's start getting that live Q&A set up here. All right. And thanks, guys. I hope that you all also have a great rest of your day, too. All right. Well, I don't see any other comments on there, so I will go ahead and start the live chat, and I will end this stream here. So I will see the rest of you guys tomorrow. Bye, guys.